Mathematics always relies on rigid rules, but when a system reaches a critical stress point, standard arithmetic fractures. Consider this rational function, x squared minus 9 divided by x minus 3. To find the behavior of this equation, the standard approach is to evaluate a specific coordinate. We want to find the exact output when x equals 3. 3 squared is 9. 9 minus 9 is 0. In the denominator, 3 minus 3 is also 0. The result is 0 divided by 0. A standard calculator identifies this as an error. Many assume the math has failed, and the coordinate is simply undefined. In calculus, this specific state is categorized as indeterminate. It represents a calculation that cannot be resolved through basic division. Extracting the truth from these mathematical dead zones requires mapping the geometry of the indeterminate form. We establish the baseline for an undefined state by examining the reciprocal function, y equals 1 divided by x. This graph shows the behavior of 1 divided by x. Evaluating at x equals 0 creates an asymptotic boundary. There is no valid numerical solution. 0 divided by 0 operates under a different logical framework. Division is the inverse of multiplication. Because 0 times 5 equals 0, 0 divided by 0 could logically equal 5. Similarly, 0 times -1 equals 0. In this framework, -1 is a valid solution. An indeterminate form represents a state possessing an infinite spectrum of valid mathematical solutions. Limit calculus isolates the single correct answer required by the specific geometry of the function. Because 0 over 0 hides the true output among infinite possibilities, we analyze the space surrounding the coordinate rather than the coordinate itself. We bypass the exact point of failure at x equals 3 to examine the surrounding data. This mathematical neighborhood is an open interval centered on 3, bounded by 3 minus h and 3 plus h. H is a vanishingly small positive number, pulling us infinitely close to the anomaly. We observe from the left at 2.99 and the right at 3.001. Inside this microscopic neighborhood, the numerator and denominator avoid becoming 0, allowing for standard division. A valid limit requires convergence. The data from both the left and right sides must point toward the same numerical target. The math behaves like a laminar stream, parting to flow around an obstruction before seamlessly recombining on the other side. A limit is a precise projection derived from neighborhood data, describing the function's behavior near a point of failure. Convergence is the standard. However, neighborhood data can also deviate, accelerating toward higher values without a fixed target. In the function y equals 1 over x squared, the neighborhood of 0 shows a specific trend. The output from both sides approaches the vertical asymptote at an accelerating rate. Both pathways lead toward positive infinity. It is common to assume that the final answer for this limit is simply infinity. We must apply the rule of convergence. A limit must resolve to a unique, constant numerical value to be considered valid. Infinity is a conceptual representation of scale. It is not a fixed coordinate. Because it is boundless, it lacks the uniqueness required for a limit. Any limit resolving to infinity formally does not exist. Calculus requires a finite coordinate. Resolving more complex functions requires algorithmic interventions to identify a solvable state. Direct substitution identifies the presence of an error, but resolving it requires classifying the specific category of the indeterminate form. There are 7 distinct indeterminate forms. These are the specific patterns of architectural failure in an equation. The pure fractional forms, 0 over 0 and infinity over infinity, are the primary targets for L'Hopital's rule. L'Hopital's rule differentiates the numerator and denominator separately to bypass the fracture point. Consider sine of x to the power of tangent of x. As x approaches 0, the function resolves to 0 to the power of 0. This exponential structure cannot be evaluated using L'Hopital's rule because it does not possess a fractional geometry. We must restructure the expression's geometry to create a solvable form. Applying the natural logarithm allows us to reposition the exponent as a coefficient. This transforms the equation into a multiplicative state, 0 times infinity. We then invert the tangent, moving it to the denominator as a cotangent. The expression is now a pure fraction. Solving limits is a process of manipulating the underlying structure of a fraction until the indeterminacy is removed. We return to our original equation, x squared minus 9 divided by x minus 3. Through factorization, we see that this fraction describes a straight line. However, there is a physical hole in the line at the coordinates 3, 6. While the exact value at x equals 3 is missing, the neighborhood limit projects a value of 6. When we apply that limit value to the empty coordinate, the line becomes whole. This relationship is the basis of continuity. The limit of a function as x approaches a must equal the actual functional value at a. Continuity exists only when the projected neighborhood data and the exact functional reality are identical. Ultimately, calculus provides the precise analytical framework required to fully map the continuous geometry that remains hidden behind arithmetic failures.